Okay, so now I'm going to talk about the concept of magnetic force. Later, once we've gone through this topic on magnetic force, we'll cover the concept of magnetic torque. So you need to memorize this important equation here. B equals to mu H, where B is the magnetic flux density. The unit is Weber per meter squared or Tesla, and H is the magnetic field intensity, and the unit is ampere per meter. So density refers to how close the magnetic flux is with each other, and the magnetic field intensity refers to the strength of the magnetic field. And B and H can be determined by this equation, where mu is the permeability. So permeability refers to the ability of a material to be magnetized and to sustain its magnetized condition. Okay, so if you compare this equation, it has some similarity with the equation that you have already learned in electrostatics, which is D equals to epsilon E. So if you compare side by side, you can see the similarity. One is for electric field, one is for magnetic field. So D is equivalent to B, where D is the electric flux density. The unit is coulomb per meter squared. So you can see the similarities. Both are measured in the unit per meter squared. So one measure the charge, one measure the magnetic flux. And we have E. E refers to the strength of the electric field. So when we compare, the strength of electric field is measured in volt per meter, and the strength of magnetic field is measured in ampere per meter. And we can find D from E or E from D using this equation here, where epsilon is the permittivity. So when we talk about magnetic force, we need to first understand the concept of magnetostatics. So magnetostatics are static magnetic fields. So static magnetic fields are produced by steady currents, and we have the symbol here J. We have already learned about J previously, where J is called the current density, and the unit is ampere per meter squared. So when we integrate the current density over a surface area, we can cancel the meter squared term to find the magnitude of current, ampere. Right? So we have already learned this equation, I equals to the surface integral of J. So these are examples of static magnetic field sources. So number one is a permanent magnet. The typical bar magnet that you see that has north pole and south pole, that is called a permanent magnet. And then we have the Earth's magnetic field generated from the Earth's core, also is a static magnetic field. And more commonly to us is this last example here, which is electricity with DC current. So when a DC current flows through a conductor, it will generate a magnetic field around it. And the magnetic field will be constant because the current is constant. So in this case, we call it as a static magnetic field source. So we need to understand how to use this equation. So this equation states that the magnetic force is equal to Q U cross B. Now, if you want to find the magnetic force of a charge, so first we need to know the magnitude and the polarity of the charge. So this is given by Q. And then we need to know U. U is the velocity or speed of the charge. And the unit is meter per second. So in other words, from this equation, we know that the charge needs to be moving for it to generate a magnetic force. If the charge is static, then there will be no speed. And if there is no speed, then the magnetic force will be zero. And the second term, B, is the third term, sorry, is the magnetic flux density. So the unit is either Weber per meter squared or Tesla. So this is a cross product between U cross B, and you need to recall from vector calculus this relationship here. So if we cross product the same direction, we will get 0. And if we cross product different direction, we will get the following equations here. So for example, if we have AX cross AY, we are going to get AZ, and so on. Okay, so an easy way to memorize is by utilizing this relationship here. We take the direction as clockwise. So if we have AX cross AY, we are going to get AZ. If we have AY cross AZ, we are going to get AX, and so on. But if we reverse the process, let's say we have AY cross AX, then we will have negative AZ. So the position is important. You cannot swap the values here because you will get the wrong answer if you do so. Okay, so let's look at an example to determine and understand more about the direction of the magnetic force. So let's say we have two charges. One is a proton, one is an electron. Both are moving in the positive X direction. And they are passing through a magnetic flux that is moving in the positive Z direction. Now, as you can see by the figure, you see that the direction of the force is opposite. This is because if you look at the equation, you'll see that first of all, U cross B, so U is in the direction of positive X, so AX, and B is in the direction of positive Z, so AZ. So we have AX cross AZ equals to negative AY. But for the positive charge, since the charge is positive, so positive multiplied with negative, we are going to get negative. That's why it's moving downwards. While for the electron, it has a negative charge. So negative multiplied with the negative here, we are going to get positive Y. That's why it's moving upward. Okay, so the polarity of the charge is also important. Now, let's look at another relationship if we want to find what is the magnitude of the magnetic force. So we know from cross product that if we have A cross B is going to be equals to magnitude A multiplied by magnitude B times sine theta. So since the equation here we have Q cross B, so we can take the magnetic force, magnitude of magnetic force equals to Q UB sine theta. So where theta is the angle between the movement of the charge and the magnetic flux. As you can already imagine, if theta is 0, the sine theta will be 0, so the magnetic force will be 0. In other words, if the charge is moving in the same direction or 180 degrees opposite direction of the magnetic flux, then the magnetic force will be 0. And the magnetic force will be maximum if sine theta equals to 1. So sine theta can be equal to 1 when theta is 90 degrees. So in other words, when the magnetic flux is perpendicular to the direction of the moving charge, we will get maximum magnetic force. If the charge is moving in both an electric field and magnetic field, then we can generate an electromagnetic force. And to find it, we combine how to calculate electric force with how to calculate the magnetic force, and we get the equation here, and this equation is known as the Lorentz force. So there are three major differences between electric force and magnetic force. So number one, electric force is always in the direction of electric field. but magnetic force is always 90 degrees to magnetic field. We are talking about maximum value. Okay. Number 2, electric force is acted to both stationary and moving charge. But as we have already proven earlier, magnetic force can only be generated when the charge moves. And number 3, the electric force gives work to a particle, but magnetic force does not give work. It can only change the direction of a particle. So because it does not give any work, it cannot change the speed of a particle, only the direction. So let's look at 2 simple examples. Number 1, an electron moving in the negative x direction, 90 degrees to a magnetic field, experiences a deflection in the negative z direction. So what is the direction of the magnetic field? So we write down the equation, Fm equals to Qu cross B. So Q is electron, so negative. U in the direction of negative x, so negative Ax. And the magnetic field experiences a force, which is in the direction of negative Az. So negative multiplied by negative, we get positive. So we need to ask ourselves, what do we value that when we multiply Ax, cross that value, we get negative Az. And by referring to the cross product relationship, we'll find that the answer is negative y direction. This should be the direction of the magnetic field. For question number 2, we have a proton moving with this speed, passing through a magnetic flux density of this 2.5 Tesla, and experiences a force of this value here. So what is the angle between the magnetic field and the proton's velocity? So the answer is straightforward. We apply the equation to define or to calculate the magnitude of magnetic force and find the value of theta equals to 30 degrees. Now, previously we studied about a charge, but what if we have a current? Now, previously the equation is Fm equals to Q U cross B. But now since we have a current and the current passes through a wire, so we modify the equation to get dFm, the differential form of the magnetic force, equals to I. So the charge Q we replace with I, and U, the speed of the charge, we replace with dL. That means the differential length of the wire where the charge is moving, where the current is moving. And then cross product with B. So we integrate both sides of the equation. So the differential part here disappear, we get Fm. And we integrate this part here, because I is a constant, we can take it out. And we need to apply a closed line integral. Why we have closed line integral? Because current can only flow in a closed circuit. So we need to calculate the closed line integral. So we have this equation here if you want to calculate the magnetic force in a current element. Okay. In the case where B is constant, in the sense that it resides externally, then we can take B outside of the integral and we find that the magnetic force is going to be equals to 0. Okay, so basically it states that the total magnetic force on any closed current loop in a uniform magnetic field is always 0. So you see the relationship here. If we have a very thin conductor and in the first initial condition we don't pass any current through it, and this here B is the magnetic flux. When we have a circle and a cross in the middle, this means that the magnetic flux is moving into the page. Okay, so this is actually three-dimensional drawing, but draw in a two-dimensional surface. So we'll see that when the current is moving upwards, it's going to be bent to the left if it's a thin conductor. And if we change the direction of the current, the direction of the force will also change to the opposite direction. Okay, so